Good morning, Peter. Bonsoir. Uh, Using energy more efficiently is indeed half of historic, and IPCC says 40 to 70% of future decarbonization. That's where most of the energy system's white space and lucrative opportunity is. And today, as renewable energy spreads around the world with astounding speed, it's all the more important to emphasize, again, the other half of the climate solution space, bringing a lot more work from the energy we use. And that makes the fossil fuel displacement very much faster, cheaper, and easier. Now, specifically, and especially for those of you who might not have run into this before, I want to describe today a proven way to make the energy efficiency resource several-fold bigger than officially supposed, and yet cheaper, and often with increasing returns. So the more you buy, the cheaper it gets. It's called integrative design, and it optimizes whole systems for multiple benefits rather than isolated parts for single benefits. This requires us to consider not just technologies, but also how the technologies are chosen, combined, timed, and sequenced. In other words, design. I'm not referring here to saving fossil fuels by substituting electricity or making electricity more efficiently by the means shown in the 3 columns here. Let's start on the left. At the upper left, the huge conversion losses in red in thermal power plants are eliminated at the lower left when solar and wind power in green generate electricity directly without a steam cycle. Now let's move to the middle column. Fuel combustion at the top provides heat several-fold less efficiently than a renewably powered heat pump at the bottom, concentrating free low-temperature heat. And then in the right column, gasoline and diesel engines with their big losses in red are much less efficient than renewably powered motors at the lower right in battery electric vehicles. So the systems across the lower row, replacing fossil fuels with renewable electricity, are several-fold more efficient in turning renewable electricity into delivered services. But this does not yet include higher efficiency in the equipment being powered, or the building being heated, or the vehicle being moved. First, doing that end-use efficiency makes the heat pumps and EV batteries smaller, cheaper, less mineral intensive. And both these kinds of efficiency, the upstream and the end-use downstream part, multiply to make up primary energy efficiency. And by that crude metric, in 1975, US government and industry all insisted that the energy needed to make $1 of GDP could never go down. A year later, I heretically suggested it could drop 72% in the next 50 years. Through 2022, it dropped 61% in 47 years. And yet, just the innovations already added by 2010 can save another 3-fold, twice what I originally thought, at 1/3 the real cost. And now, 14 years later, that's looking quite conservative. And that's because optimizing buildings, vehicles, and factories as whole systems, not as piles of little parts, can often make very big energy savings cost less than small or no savings, turning diminishing returns into increasing returns. A little more history. In the past 47 years, saved US energy, about 2/3 of it from smarter technologies, has accumulated immense energy savings. Meanwhile, renewable energy nearly tripled, but with 27 times less cumulative impact. Who knew? Renewables get virtually all the headlines because they're visible on the rooftop, on the skyline, but energy is invisible, and the energy you don't use is almost unimaginable. So let me help you envisage revolutionary efficiency through a few practical examples. My wife and I live 2,200 meters above sea level near Aspen, Colorado, where the temperatures used to dip as low as minus 44°C, minus 47°F. And we've seen up to 39 days of continuous midwinter cloud. Yet our house has no heating system, and that made it cheaper to build 40 years ago because we saved more construction costs by not needing a heating system than we paid extra for the efficiencies that got rid of the heating system. We just harvested our 81st passive solar banana crop. You can see some banana jungle behind me, perhaps. And saving 99% of our space and water heating energy, 90% of the electricity, and half the water, all paid back in 10 months using 40-year-old technology. Today's, of course, is much better and cheaper. And an analogous approach works fine in Bangkok. Almost everyone on Earth lives in a climate somewhere between those of Bangkok and Old Snowmass. And I mentioned many benefits from each expenditure. Behind me is this white arch you see in the top of the upper middle photo. Well, it actually does 12 different things, but it has only one cost. This building has curvy walls. There are 8 or 9 reasons for that, but we only pay for them once. Now, the best buildings' energy intensities in green have fallen rapidly. Our integrative design of the Empire State Building saved 38, later 43% of its energy with a 3-year payback. Our cost-effective Denver retrofit soon saved 70%, beating what was then the best new U.S. office. That's only a third as efficient as RMI's office 10 minutes from here, and a Bavarian building uses 2/5 less energy still. What's mainly improved is not so much technology as design. IPCC reported decade-old data from the best European new buildings on the left and retrofits on the right. And in both graphs, the bigger savings are toward the right and the cheaper savings are toward the bottom. These buildings saved up to at least 90% of their energy use without costing more per unit of saved energy. There is a lot of vertical cost scatter. That just shows the business opportunity of conforming inferior projects to best practice, because whatever exists is possible. And now there are some new super outsolation techniques that can rapidly retrofit many existing residential or commercial buildings cost effectively to net zero energy, even without disturbing the occupants. Let's see if I can show you a little 1-minute video of this from Holland. Oops. How do I run this? Yeah. So this shows how an energy strong retrofit floods your house in a factory customized super insulated T-cozy. It drops in an efficient heat pump HVAC core and then a super insulated photovoltaic roof. And as shown here, it can be installed even in a single day while you're off at work. There was a German project that recently retrofitted super outsolation onto a major facade in 20 minutes. And once this is all done, you pay off the retrofit cost instead of a perpetual utility bill. And in some modest number of years, it's paid off, you own it, there's a long-term warranty. More than 16,000 of these energy strong or energy jump or leapfrog retrofits have been installed in Holland, Britain, France, Germany, Italy, thanks to coordinated reforms in building organizations, manufacturing, finance, and regulation. Now there are pilot projects underway in New York, Minnesota, Massachusetts, and California, where my colleague Martha Campbell leads the Realize Consortium. Its aims include scaling to retrofit California's 0.4 million low-income housing units and ultimately all 13.5 million housing units statewide. So if you're intrigued about this super outsolation industrialized technique, find out about the new global Energy Sprong Alliance. That's spelled ENERGIESPRONG, all one word, and it's at energysprong.org. So you see, this is just about getting done, adding the super outsolation and new facade over the old brick. And you can also, in some of these shots, see the house next door that has not been so treated. This is a new front entryway going in. Provide more of a airlock and extra storage space. I don't think these are what I would call super windows up in the R10 or 12 center glass range, or 14. In our house, most of ours are 14, the best ones are 20. With 4 or 6 elective surfaces and heavy gas bill. Now you see the old on the left and new on the right, and the photovoltaics meet all the annual energy needs. Okay. Now let me go to the opposite kind of climate. In 6 muggy Indian cities, 1.5 million square meters of integratively designed offices that Peter's helped a lot with, use up to 80% less energy than the Indian norm, but with about 10 or 20% lower construction cost, 60% less cooling capacity, and yet superior comfort and satisfaction. Glare-free daylighting, like you see in that big floor plate on the right, is delivered throughout by contract. If workers complain of glare and demand blinds, then the architect doesn't get paid. And the HVAC systems are about 3 times more efficient than the norm in Singapore, and yet they cost less and they work better. However, we can next eliminate refrigerative air conditioning. In this shaded pavilion, like a little bus stop shelter open at the ends, Singaporeans stayed comfortable outdoors without cooling, drying, or moving the hot, still humid air. At 32C or 90F and 80% relative humidity, their body's far infrared radiation was absorbed by panels shielded by a thin plastic film to keep the moist air away from the cool surface. And the surface is cooled to 23 to 25C, that's 73 to 77F, by circulating water. Well, you can now cool that water with special radiant roof surfaces, even in full sunlight or under cloud or in the monsoon, using no electricity. And if this approach can be made cheap and vernacular enough to retrofit into the world's hot climate apartments and slum dwellings, that could potentially eliminate the global growth in peak electricity demand. So this is a big deal. Inside buildings, here's a fist-sized Swiss heat pump that can deliver 6 to 15 units of hot water per unit of electricity. Panama mentioned heat pumps are getting a lot better. Well, I'd like to see them all like this. And here's a Swiss electric cooking system with vacuum insulated pots. It's better and 2 to 4.5 times more efficient than induction cooking. It is unfortunately not really available in the market because of problems with the small manufacturing company in Switzerland. I hope those might be solved. And if, by the way, somebody commercializes the biradiant ovens that Purdue developed in the 70s and combined it with such an efficient cooktop, you could retrofit from gas oven and stove to all electric with a single 30 amp 117 volt circuit and not need to retrofit 240 volts. Another good entrepreneurial opportunity. I want to go a little bit beyond buildings to give you the bigger picture of demand side decarbonization. In industry, RMI's 60 odd billion worth of integrative designs for big companies worldwide typically found in these retrofits about a 30 to 60% energy saving, paying back in a few years, and much better than the normal ESCO delivery of disintegrated design in that colored oval in the upper left. In new factories, we typically found 40 to 90+% energy savings with almost always lower capital cost. And a lot of this was just from paying attention to fundamentals that are often neglected. For example, motors use half the world's electricity, more in industry. Half the motor power runs pumps and fans. But if you redesign pipes and ducts, you can save 80 to 90+% of their friction. That would, if everybody did it, save a fifth of the world's electricity and typically pay back in less than a year in industrial retrofits and instantly in new builds. So low friction pipes make the blue pipes tiny. And notice on the right, we're raising the pump up to the pipe, avoiding 4 right angle bends from the normal practice of dropping the pipe down to a pump on the floor and back up again. Then if you lay out pipes before equipment, you stagger the 10 chillers from a neat row to eliminate pipe elbows. Friction and capital cost fall, and yet such rearrangement of designers' metal furniture remains largely unnoticed and unpracticed. It's not in any standard engineering textbook, industry forecast, government study, or climate model. Why not? Because it's not a technology, it's a design method. And few people yet think of design as a scaling vector, a way to make big changes fast. So now I'm writing, and Peter's helping with an illustrated how-to manual for Chinese factory engineers called the Tao of Pipes, which I'll be getting out this year. Now, think for a minute about the whole power and pumping system. From the fuel burned in the thermal power station to the end use, many successive losses compound, and therefore only about 1/10 of the energy in the fuel comes out the pipe as flow. But if you now turn those compounding losses around backwards from right to left, they become compounding savings. And every unit of flow or friction you save in the pipe saves 10 units of fuel cost, emissions, and what Hunter Lovins calls global weirding back at the power plant. And as you go back upstream, the components get smaller and cheaper. So the total capital cost goes down. Of course, this also works fine in buildings. And of course, once your pump or fan needs 5 or 10 times less torque, you can replace the big inefficient motor system with a new right-size, super efficient, tiny one, and save about half the remaining energy by 35 integrated improvements to that motor system. And of those, 28 are free byproducts of the first 7. So then you end up saving twice as much drive system energy as the usual 2 or 3 disintegrated improvements at about 1/5 their unit cost. And the potential fraction of global electricity savable in fluid handling goes from about 1/5 up to about 1/3 when you include the associated drive systems. Now, before we make industrial process heat less or cooler or cleaner and material flows circular, we ought to be using materials efficiently. A couple of papers I wrote 3 years ago, one on technology and design, the other on new business models, showed how buildings 1/2 of cement and 1/3 of steel is largely wasted by inefficient structural design. So tension structures can save about 80 or 90% compared to compression structures. Pouring concrete into fabric rather than prismatic forms can save half. Concrete bridges support mainly their own weight, but 3D printing an airy dendritic structure supports mainly payload. Corrugating a thin concrete floor slab can make it 4-fold lighter, and floor slabs are half the weight of a typical mid or high-rise buildings, not even counting the beams and columns and footers to hold it all up. By the way, this change also eliminates the steel. And by the way, we may end up making iron and other primary metals with electrochemistry, not with green hydrogen. Now, passive design and thin floor slabs can fit 3 stories with a normal 2.8 meter ceiling height into the vertical space of 2 stories for 55% more floor space, 15% less core materials, 9% less glazing, lower cost. Why would you build any other way? Another example, again, just to round out your picture of where integrative design can decarbonize things, is doubling or tripling automotive efficiency before electrification. Because 2/3 of the energy you need to move a car is caused by its weight. And even at 2013 prices for carbon fiber, BMW showed how integrative design can lightweight a car at competitive cost. This i3 that I drive reportedly made money from the first unit off the assembly line, and its carbon fiber was paid for by the batteries that its lightness saves. Fewer batteries also mean faster recharging with less investment in charging infrastructure. Such an integrative design snowballs weight savings a lot more than usually assumed. The manufacturing is radically frugal. It confirms the elimination of the 2 hardest and costliest steps in making the car. It's much better for workers. And such efficiency in US electric cars could save over $200 billion a year. And if that's for quadrupled efficiency without compromise, and a lot of other benefits. My favorite is half normal turn radius. And of course, the innovation doesn't stop there. 2 electric hypercars, both from little firms I advise, are ready to start production as soon as they finish raising capital for it. And their cars are 2 or 3 times more efficient than even a Tesla. So the solar cells on top of these efficient cars can capture enough energy for normal daily driving without having to plug in. Wow. Tesla's semi-electric truck is 3 to 6 times more efficient than normal. Here's a quiet double-range diesel air taxi. It can take you from Aspen to London with 1/8 the operating cost and fuel use of a normal business jet. And its laminar aerodynamics can scale up. So aviation offers an astonishing suite of opportunities that co-evolve with mutually supportive ones in the automotive world. For example, the best aviation motor produces 25 kilowatts continuously per kilogram. That's 5 or 10 times the power density of a standard electric car motor. And it's made by Toyota's electrical supplier, Denso. Now there are new lattice and membrane structures that can make aeronautical structures 98% lighter. Now you may wonder if all this stuff is possible, and yes, it is. Cite you chapter and verse. Why is the world saving energy only about 2% a year instead of twice that fast as many countries now agreed, or faster? Some big companies that paid attention sustained 6 to 16% energy savings every year for years. Well, energy efficiency gets little attention and respect for at least 20 tedious reasons, plus specialized ones in each end-use sector. And my Stanford class takes about 2 hours just to list these obstacles and the opportunities they can be turned into. Each line of this can merit a whole seminar. We can't do that here, but in general, these are not the familiar obstacles or solutions that policymakers have gotten good at with renewables. They're a whole new set that needs similar insight, tenacity, entrepreneurship, but applied in different contexts and scales. It's a whole new world of barriers and opportunities. And most of efficiency's practical needs are systematically neglected because very few policymakers grasp the size of the prize. It's severalfold bigger but cheaper than they thought. Demand-side decarbonization is usually cheaper and may well be faster than supply side decarbonization, especially if we can spread integrative designs by images and memes over social media. Efficiency's risk portfolio is a lot more diversified than that of wind or solar. There are more workarounds, more ways to evade obstructions. Efficiency can be more pervasive, bottom up, granular, accessible, equitable, benign. That's all good. It deserves our attention and our skill and our juice. Now, my Stanford lectures in CEE 107R and 207R, for any of you around to consider taking it in the winter or spring quarters, offer hundreds of such cases and opportunities across all sectors and most uses. And if you add them all up, such proven innovations, without counting the savings that Panama described from electrification and renewables, could about triple global end-use energy efficiency by 2040 and about quintuple it by 2060, all at a pace within the forecast envelope of the International Energy Agency. If we can quickly make integrative design the standard practice everywhere. So to achieve quintupled efficiency, or what you might call 5 eta, named by analogy to 6 sigma, we've identified about 20 scaling vectors that I would like to test and spread. So let me invite each of you to join the fun. Let's go forth, be fruitful, and subtract. Thank you.
Thank you, Amory. Again, very exciting. Lindsay, do we have any questions? Or if you haven't typed in a question in chat, now would be a great time.
Yeah, there aren't any presently.
I'm happy I said nothing controversial.
Amory, maybe you can give us a little bit of insight on integrative design, and it sounds like to me you're seeing a lot of barriers to integrative design, but when you're talking to students and or other folks in the building industry, what's the reception that you're getting?
Well, we do this with all our clients on design projects in all sectors, and they all pick it up, learn it fast, and do it successfully. I can't think of a case where it hasn't proven teachable and adoptable. Of course, you may have to convince people. I mean, you in your own practice experience this all the time, where you lay out pipes in a way that works a lot better but looks really weird. And then you have to spend a lot of time explaining to the client why it doesn't look like what they're used to. You don't get paid for doing that, and your margin vanishes into client education. Wow, what an incentive to do good design. So we all have a lot of work to do in educating clients as to what's possible, but there are some design firms that are doing this successfully. For example, one that's hired away quite a few people from RMI, and we're happy to share them, is McKinstry in the Pacific Northwest. They do a lot of big industrial facilities, including many in IT and manufacturing. And I understand they are doing very well practicing integrative design, and gradually consciousness is spreading among the client communities that this is really a good idea. Don't worry if it looks different. Just watch what happens to your bottom line.
Great. What's the response that you get when you're, if you think back to when you started proposing these ideas in the 70s and 80s, and a lot of people were saying, no, it's not possible. How does it compare to where we are now?
We don't hear much of the "it's not possible." And if somebody really thinks it's not possible, we're happy to work with their competitors, and they'll get to understand it that way. So we use competition to do a lot of our outreach, and that works just fine. I'm 76 now. I don't spend a lot of time preaching to the unconverted and trying to convince people to do what would be very advantageous to them. I just work with the early adopters, one or two in each sector, firms that are respected and feared for their competitive prowess. And things don't always work out. Sometimes the chairman you're working for dies or retires, or the wonderful engineer you're working with goes somewhere else. So you need a diversified risk portfolio. And we've had a number of projects fail for those kinds of reasons. But we think we are making good progress. And I noticed there's a question coming up about designer aesthetics. It's a funny thing. Why do standard practices and indeed some codes require orthogonal pipe and duct layout, everything dressed at neat right angles? Because it's easy to draw. Huh? We don't draw it anymore. The computer does that. Why doesn't our design software have a toggle to let us do non-orthogonal pipe layout? Run diagonals, run interesting big sweep curves, sweep bends, design out elbows and bends all together. Well, good question. I think you can, in the main set of products, you can do that non-orthogonal layout, but only with third-party add-ins. That needs to get fixed. But I don't think what we're doing has to make any buildings ugly. Quite the contrary. The building can look like whatever you want in whatever built form and materials and building methods and climate and culture you have. It just won't make noises. It won't emit stuff at you. It'll cost probably less to build. If it costs more, it's only by 1% or 2%. And that tends to go away with experience. So we're now in the +2% to -2% range on German passive houses after they've done a lot of them. And aesthetics can be unchanged, or if you wish, enhanced. You can do a lot, for example, with glazings that you might not be able to do in conventional design without unreasonable burdens on operating cost and HVAC capacity. Oh, I'm sorry.
Wonderful.
The writer meant ethics, not aesthetic. Well, that's interesting. Designer ethics. Well, maybe we do need to do a better job of teaching it, but I'm not clear what the ethical issue might be. Peter, how do you interpret that?
Well, I interpret it as the designer community that we're teaching, the ethic of the impact of your work as far as climate change and such. I don't think that there's much discussion about that in most educational forums.
So we're leaving out some important ethical drivers that serious designers will want to think about. There is a and Eric says, in my experience, some designers don't take responsibility or try hard enough. True. Any like that, you know who you are. And if you don't, you might learn from competition. There's a nice question from someone named Zimmerman that pointing out that passive systems like geothermal heat exchange can be adequate for 80% of climate conditions and then rely on supplemental heating or cooling for the extremes. This approach often gets dismissed as excessive first cost, that is integration of multiple mechanical systems. Well, I think there are probably cases where you're right, and that would be a good deal. On the other hand, what you ought to be comparing it with is making the building so efficient, like this one 40 years old, that it doesn't need heating and cooling. And that's probably in many cases, if not most, going to be cheaper than geothermal heat exchange. But you're welcome to go hunt for exceptions.
So last question from Monica, what role do you see the contractor community playing here? What do you hope to see more of?
Oh, enormous. And that's why I'd like to figure out better outreach to the contracting world, because, you know, half of HVAC equipment, more or less, in the US is not designed by design professionals. It's designed by the contractor, the installer, from traditional knowledge handed down. And I think we can improve that nicely. In fact, in our house, I needed to add some plumbing, and our master plumber said, okay, to circulate your surplus solar hot water to your floor slabs you put in 82, in case you'd ever need them, for the last 1% of your heating, yeah, I'll just get you a primary pump and 6 zonal secondary pumps. I said, well, that sounds like a lot of pumping. He said, oh no, it's trivial. It's 2.3 or 4 kilowatts. I said, that's way over twice what the whole building, mainly IT, uses for everything. Let's talk about low friction pipe layout. So in a half-hour tutorial, he got into low friction pipe layout, and we ended up with a maximum of 43 watts, not much of the time, and 97% saving in pumping power and energy, and a big saving, of course, in capital costs, because I used one little pump instead of 7 bigger ones. I paid a little more for unusual pipe layouts, but there was less piping altogether. Well, that showed me it was really teachable, because I wouldn't have said he was a highly innovative plumber. There are a lot of really smart plumbers out there who, if they saw pictures of great layout, would say, yeah, I could do that. I could be a hero. I could provide a much better value proposition to my customers. And I think that sort of thing can spread pretty quickly, whether in big or small firms or sole practitioners. So that's what I would love help from this group in figuring out how to spread. And I'm A.B. Lovins at stanford.edu. If you have ideas, please write me.